Hello and welcome to 11.7 for your enjoyment and challenge. This week we'll be working on ratio of areas. If we have some squares here and we have a 2 by 2 square, obviously our area is going to be 4. And the idea here is that if we double the lengths of the sides, initially you may just think that the area would double as well, but when you actually look at it, the 2 by 2 turns into a 4 by 4. So the area does not double. So the sides will double, but the area quadruples. Similarly down here, we're going to double the sides. We're going to kind of check out what happens here. 3 by 3, this will be a 9. And then the area would be a 36. So notice that if the sides doubled, the area quadrupled. Which leads us to some more questions about what happens here. Like what if you tripled the sides? Well, let's take a look here. So if we bumped it up to 6 by 6, we would get the 36 again. And notice from here, if we tripled, the area went up by times 9. So we get the idea of if we times 2, area is times 4. If we times 3, the area multiplied by 9. So what's happening is, whatever is happening to this side, the area is essentially the square of that. So if we are multiplying by 2, the area gets multiplied by 2 squared. Multiplying by 3, the area gets multiplied by 3 squared. Which kind of makes sense because we're changing each dimension. So if we're doubling the base, we're also doubling the height. And that's where our main theorem from this section comes in, called the similar figures theorem. If two figures are similar, the ratio of their areas equals the square of the ratio of their corresponding segments. So here's some example questions. If the area of figure A is 20, what is the area of figure B if the ratio of the sides from A to B is 2 to 3? So if a side is 2 to 3, that means that the area's ratio is not 2 to 3, but is in fact the square of that. The area of the ratios must be in a ratio of 4 to 9. That will help us create a proportion to solve. So we can get 4 over 9 would then equal 20 over x, because we're looking for A compared to B. And using some means extremes product theorem, we can multiply 4 by x and 9 by 20 and solve it and find out that the area of figure B is in fact 45 centimeters squared. Let's take a look at number 2. If the ratio of the side lengths of two figures is 3 to 4, what is the ratio of the areas? It's actually simpler than the first one. So if the sides were 3 to 4, the areas would therefore just be in a ratio of squaring of that, 9 to 16. It's kind of like just the first part of the first one. I'm going to move on to slightly more challenging ones here. Number 3, if the ratio of the areas of two regular dodecagons is 24 to 27, we're going to find the ratio of the perimeters. So it doesn't really matter that it's a 10-sided shape. We know that these two shapes are similar because they're both regular and their sides are in ratio. So their angles are congruent because they're the same side of shape, and their sides are in ratio. So they're definitely similar. So we know that the side, if we take either side, square it, we'll get the ratio of the areas. But here we're given the ratio of the areas, so we're working backwards here. So if the areas are 24 to 27, if we want to work backwards, we're not going to square it, but we're actually going to square root the entire thing. So then we're going to deal with some calculation from Algebra 1. The square root of 24 can be simplified into 2 root 6. The square root of 27 would be 3 root 3. And can we simplify that any more? Let's see, we got this right here, root 6 over root 3 would just be root 2, right? So we'll have the coefficients there won't really simplify, so we have 2/3, but then the other ones become just root 2 in the numerator. So it'll be 2 root 2 over 3 as it's simplified 1. Notice that would give us the ratio of each segment, each side. But then if we're looking for the perimeter, it's in fact just going to be the same thing. Because if each side is in this ratio, the entire perimeter will lie in the same ratio. And now we got some ones that are a little bit strange. We're looking to find the ratio of the areas of region 1 compared to region 2. So looking for the ratio of this area compared to this area, which does get cut off right here. So that's a little bit strange. And we're only given 8 and 10. Yet again, 10 also does get cut off here in this picture, which should kind of make sense given it. So what we have to look for here is similar figures. So 1 is not similar to 2 because they're definitely two different shapes. 1 is a triangle, 2 is a trapezoid actually because that's the parallel sides. But I could compare 1 ratio, I could compare 1 to the entire thing, 1 plus 2, the entire figure, because they're both triangles. So I don't know what we want to call that here. We can just call it 3, I guess. 1 and 2 together. That could be interesting. And why are they similar? Because they're both triangles and they have the angle-angle theorem, because they would have this angle in common. And we actually know that this angle is congruent to that angle because they're corresponding. We also have the third angle as well. So we have the chapter 8 theorem. So now we can compare one of the sides. If I look at triangle 1, I have a side of 8. The corresponding side in the big triangle, known as 3 that we made up, would be 18. So the sides are in an 8 to 18 ratio while the angles are congruent. So that's the ratio of the sides. But we want to get the ratio of the areas. So we're going to square that. Notice I did simplify 8 over 18 first. That always makes things a little bit nicer. And then we square it. And we're going to get 16 over 81. So that is the ratio of the areas from 1 to the entire thing. But I just want section 2. So section 1 is definitely 16. Section 2, though, would be the whole thing of 81, taking out the 16 from up top. Okay? And that's going to get your final answer. The ratio from region 1 to region 2 is 16 over 65. That is a little bit sneaky. We're going to see that happen again in the next example. You could pause this and try this on your own first before seeing it. So that way you get kind of used to this. A little bit unusual here, but that's kind of how you can get just that region down here, not the entire thing. So in this one, we're looking to compare again region 1 to region 2. It's definitely split at this point. Initially, the two shapes are not similar. So we are going to compare region 1 to the entire region. Okay, 1 and 2 together because they're both triangles. They have an angle in common, and they have another angle that's given to us to be congruent. So we definitely satisfy the theorem, angle-angle. And now we can compare it. We have to make sure we match up our corresponding sides a little bit, because I kind of think this gets rotated, or maybe reflected, because this angle needs to flip over. So the 3 does not match this whole side. When the 3 gets flipped, so the angles match, 3 compares to 7. So from region 1 to the entire is 3 to 7. That is a side. However, we need to get to the areas, so we're going to square it, which will yield 9 over 49. But that is yet again the area of region 1 compared to the entire. But if we want to compare it just to 2, we need to get rid of area 1 from the entire. So we need to subtract 9 off of it. That will give us our final answer of ratio is 9/40. And now we're on the back for number 5. I'm looking to find the ratio of the areas of a triangle ABD, which is the large triangle, compared to CED, which is the smaller one. Chances are they're similar given this question, but we got to make sure. They both have a right angle, so both right and congruent, so E maps to D. And since they're overlapping, they actually have an angle in common, which is angle D over here. So we appear to have enough to satisfy the angle-angle theorem, which we do. So they are similar. So now we got to make sure we match up the sides properly. ED is going to match. It's hard to tell because it gets dilated, possibly reflected. There's a lot going on. But ED is going to match BD, which we can tell because it's right angle to our green mark. And the one on this one will match is right angle to green mark. So ED does match BD. So we have a comparison of 10 to 15. So that's our start here. Or 15 to 10 because it asks for the larger one first. So make sure you're right in the right order. That would be the ratio of the two sides. We always want to try to simplify our sides first. That's 3 to 2. And then they get the ratio of the areas. We will then square it. And notice some of my little things, like I wrote that these two fractions are equal, but I did not write that these two fractions are equal because I squared it. So I kind of changed it to an implies. You could definitely add the parentheses and square to create a series of equal. And now number 6 is a little sneaky. We're finding the ratio of the areas of region 1 to region 2. The sneaky part about this is that triangle 1 and triangle 2, not similar. And I don't think we have an overlapping that's similar. Like 1 is not similar to the whole thing. So we have a sequence here where we do not have a similar figure. Sometimes you're still able to figure out the ratio of the areas, especially if you can find the area for both. We kind of can here, but not really. We can't get the actual area, but we could get the area in terms of a variable. Because if I draw in what would be the height, and I just call it h for height. If I look at triangle 1, my area would be 1/2 times the base of 3 times the height of h. So 1/3 times 3 times h. Triangle 2 has an area of 1/2 times 8 times h. So that becomes quite helpful, especially because I'm comparing them in a ratio and a fraction. Because look at all this simplification that will happen. The 1/2 simplify. My variable, because the height is the same, will simplify, and I'm left with 3/8. My final answer is 3/8. I don't square this one because the shapes weren't similar. Instead, I actually found the area here, in terms of h, found the area here, and then worked our way through. So that one was a little bit different, a little bit sneaky. There are 3 more practice ones on the bottom that has both of them. Somewhere you square it if they're similar. Somewhere you don't if they're not similar, and you have to use some other method. So we'll take a look at the final 3 real quick. They want you to compare the ratio of 1 to 2 and 1 to 3. So it's like double questions for the last 3. So if I'm in this one, I do not have any similar shapes. So this is actually one with the drawn height in. Fortunately, all 3 triangles have the same height. That's going to create the same setup we just saw in number 6. So when I'm comparing 1 to 2, it would be 1/2 times 8 times h, and 2 would be 1/2 times 5 times h. We just saw that that's just going to simplify out to 8/5 would be the answer to part 1. And part 2 is going to be very similar. It's comparing 8 to 15. I think it's one of the sneakiest ones on the page. It utilizes both scenarios, one with a common height and one with similar figures. When we want to compare 1 to 2, 1 to 2, not similar. There's definitely, even though we have some parallel lines here, our alternate interior takes us into triangle 3, but we don't have 2 angles in 1 and 2 that are congruent. However, if we kind of cut off this one and look at this as the base of each triangle, it has the same height up here. So like this one's height will go both heights would go from this line to that point. So they actually do have the same height. So we're going to have a base comparison one just like this one and the one before it. Regions 1 to 2 is in a ratio of 7 to 4. Regions 1 to 3 though do not have a height in common, but they look very similar. In fact, they are, because of this alternate interior going on here. So if we are now comparing each of those to each other, so, and we also have vertical in the middle. So we got to see which ones properly match up. Since they're getting crossed over, like the double to the double, the 7 actually matches to the 4. So it seems like it's 7/4, but reminder that that's segment, and now we're going to area, so we have to follow the similar figures theorem. So that one gets squared. So the second answer is 49 to 16. And here comes number 9. We do have a tough one to end this. We're looking to compare the ratio of region 1 to region 2. We do have two similar triangles here because of our square here, causing for a variety of things like parallel lines. We're going to have a right angle here. We're going to have, let's see, we'll have corresponding from here to here. So our two kind of be a little bit similar. That will kind of give us a 30 here as well. To help us out, we're going to have to label our square actually. If we call each side x, that becomes very helpful. Because if we call this one x, and then we look at this triangle here, the 30, the x matches to the 30. So that tells us that this side would be x root 3 because it will match the 60. Similarly, this one's kind of the reverse as the 30s here. The 60 is the x, so the 30 is x over root 3, which we might simplify to x root 3 over 3. And now, if we want to compare them, there's basically two ways that we can kind of look at this. We do have similar figures here. Oh, don't even need that. And let's take a look at the final question. We have just region 1 and region 2, because there's no region 3. And we're looking to compare them. These are two triangles. They appear to be similar. They will, because they both are going to have a right angle here. And these two angles are actually going to be corresponding using our parallel lines here and our transversal there. So we do have two similar. That's actually going to tell us that this angle is 30 as well. So the way to kind of do this one, there's always like a little trick for some of these. If we kind of call our square, if we call each side x, that becomes very useful. And that can help us get the base of this triangle, because if the x is across from the 30, across from the 60 will be x root 3. And that's actually all that I really need, because now I have similar figures and I can compare the base of each one segment. So my comparison is x over x root 3, which simplifies, because the x's will simplify out to 1 over root 3. But that's a ratio of the sides, so I need the ratio of the area. So I'm going to square each one. 1 squared is 1. Root 3 squared is 3. So the comparison is a 1 to 3 setup for this one. And that's it for 11.7 ratio of areas. Quite a variety of questions here, basing off the two types, the similar figures theorem, and then looking for a common height or something that overlaps can be a little bit sneaky. All right, good luck.